So you learned what your next steps could be when it comes to Python. What about the blockchain? The blockchain was just our course project to learn Python. We built quite an elaborate blockchain though. It has all the core features a typical blockchain has. It really shows you how the blockchain technology works. Nonetheless, it's not production ready. There is more you can add, and there is a reason why the Bitcoin blockchain is not developed by one person only and why its code base is a bit bigger than our blockchain here. The Bitcoin blockchain code is not written in Python, but it's open source, and if you want to have an idea of how complex it is, you'll find a link to it in the last lecture of this module. So what can you do? You can improve error handling, for example. We only got very basic error handling in our blockchain. In all the cases where errors could occur, for example, in our blockchain PY file, when we're reaching out to our nodes and we're trying to get responses from them, we often only handle one or two types of errors in a very basic way. You might want to do more there. Maybe you want to show the user a better feedback. Maybe you want to store errors in a log file. Maybe you want to also handle different types of errors. That really requires more testing from your side to find out which kinds of errors occur or could occur. And then, of course, it depends on which kind of application do you want to build. Is it important for your application to provide more feedback to the user, or does this not really matter? But that is definitely something you could dive into. You also want to have a look at scalability. Our blockchain works, but it's not really scalable that much. And that, by the way, is a problem many public blockchain projects also face, like Bitcoin. They're still working on its scalability because for now it's working, but it'll keep on hitting certain limits around which the blockchain or the Bitcoin community then has to work. What are potential scalability issues you need to address? If you have a look at our blockchain, right now our entire blockchain is stored in a list here, and then of course in a text file. So we got our blockchain list in the blockchain class, and we store all the blockchain data in a text file. Now, obviously, the bigger your blockchain gets, the more memory it will occupy when you load it into a Python list, and the longer it will take to process that list, and the bigger your text file is going to get, and the longer reading that text file will take. So things you might want to address or you could look into are using a database instead of a text file, loading only parts of the blockchain into memory, though you will then also have to find a solution for things like calculating funds correctly, validating the entire chain correctly. The bigger your blockchain gets, the more your users or your node hosts need to download, by the way. The Bitcoin blockchain is over 100 gigabytes big already, and of course it keeps on growing. Now everyone who's running a full node and who does some mining or who processes transactions typically downloads the entire chain, and that occupies a lot of space on your system. That can be a problem. You also have the bandwidth cost of downloading that entire chain. And we have that too. In our resolve function, for example, we are querying all our nodes and we are getting the complete chain from them. It's no issue here for us, but if our chain is more than 100 gigabytes big, we have to download that entire size, that entire chain from every peer node. Probably not the resolve algorithm you want to use in a real big blockchain, therefore. But still, you'll have to find a way to validate that the entire chain you're getting is valid, even though you might not be getting the entire chain. And these are all issues which are not necessarily solved yet, which are also discussed in blockchain communities, in the Bitcoin community, and where you can turn to find how other projects solve that and what you could do to improve scalability and make sure your blockchain keeps on working in the future too. We also don't have the perfect peer network connection set up in our blockchain. The broadcasting does work, but only on a basic level. You might want to improve that with scheduled broadcasting or async broadcasting in a real blockchain. Because what's the issue with our current approach? If you have a look at the blockchain PY file and there at the mine block method, for example, we do contact all peer nodes to let them know about a new block, right? The problem just is these peer nodes normally should also contact their peer nodes and let them know about the block. But we deliberately made sure that this does not happen. We made sure this does not happen in the add transaction function, to be precise, where we have is receiving, because there we have the problem. In add mine block, we don't have it, because in add block, that would be where we would have to contact our peer nodes, and we didn't implement that here. So that would be another case, though, in add block, when some other node is telling us as the peer node of that other node that it has a new block, we normally would also want to inform our peer nodes about the new block. And the same for incoming transactions. But this leads to a very long chain of us telling some other node, which then tells some other node, and so on. And if we have to wait for all these responses until we, as the node who originally mined the block, gets the response, this takes super long. So normally what you would want to implement is an approach where you add a new block or a new transaction, and then you schedule a task where this information is sent out to your peer nodes, and you don't necessarily wait for their responses instantly, but maybe you query them for their opinion at a later point of time. Or you set up some kind of WebSocket connection where you have a live connection between peers and not just a push connection as we have it. We push information to the peer nodes and we either get back a response immediately or we don't care. Now this works fine here, but for a real peer network, you might want to fine-tune this and improve this. So that's another part which can be improved, the peer node network connection. Mining difficulty is also something you can improve and change. In our blockchain, how does mining work? If we have a look at mine block, we do, of course, mine by generating a new block, and the part which takes longest here is the generation of the proof of work, which we're doing in the verification function. There we have the valid proof method, which generates a new proof of work. Now, there we get a proof number as an input and return the result, whether that leads to a valid hash or not. The difficulty here can be increased by requiring more leading zeros. And in most blockchains, you want to increase difficulty over time. The first few blocks should be added quickly, so that in case you're building a cryptocurrency, you get coins into the system quickly, you get the first blocks into the system quickly. But the longer your blockchain gets and the more coins are in the system, the longer it should typically take to mine a new block. Though you should also keep in mind that the time it takes to add a new block also impacts the time it takes to handle transactions in the end. But still, in Bitcoin, for example, the amount it takes to generate a new block increases every 100 or 1,000 blocks, and that differs from blockchain to blockchain. So that is also something you can look into, generating a dynamic difficulty, which actually increases the longer your blockchain gets. That's another thing you see in a lot of blockchain projects. And to add one last thing, not necessarily the last thing you can improve, but the last important thing I want to mention here, because you'll read it when you dive deeper into blockchains, is that for validating and analyzing transactions, you could look into using a Merkle tree. Now, right now, we verify all our transactions by going through all transactions in all blocks, and we verify each of them. Now, if you have a lot of transactions, more than 10, maybe a couple of hundreds in every block, and you get a lot of blocks, then going through all of them to verify if they're all valid, if their signatures are valid, that will take a lot. Merkle tree is essentially a way to hash verified transactions and then also to easily validate if that hash is correct and therefore validate your transactions in bulk. That's the short summary. A thread which discusses this and dives a bit deeper can also be found in the last lecture of this module. So these are just some ideas, not an exhaustive list, not necessarily everything you can do, but these are some things you should keep in mind if you want to productionize your blockchain. Building a real blockchain that works and is secure and is distributed is of course a lot of work, but all the core concepts were covered in this course. That is the important part. You should now really know how a blockchain works. And just because it's a bit harder to put it into production and to finalize it, doesn't mean that the blockchain we built here isn't realistic. It's very realistic. It has all the core features. These are things you can dive into as next steps.